Ever wondered how your email or that funny cat video gets from one side of the world to another? It all comes down to tiny digital messengers called packets and the smart devices that guide them, switches and routers. So, how do they really work? Let's dive in. Imagine a small office network. You have a few computers and a printer, all connected to a single device called a switch. When your computer wants to send a file to the printer, it creates a data packet. This packet is like a letter, and on its envelope, it has a destination address, not a street address, but a MAC address, which is a unique hardware ID for every device. The switch receives this packet and looks at its internal address book, called a MAC address table. This table tells the switch exactly which port the printer is connected to. Instead of shouting to everyone, the switch smartly forwards the packet only to the printer's port. It's efficient and keeps the network traffic clean. But what if the switch doesn't know where the printer is? This happens with new devices or when the table is cleared. In that case, the switch does something called flooding. It sends the packet out to every single device connected to it, asking, "Who has this MAC address?" The printer replies, "That's me." The switch then learns the printer's location, adds it to its MAC address table, and remembers it for next time. It's a bit noisy at first, but it's a quick learner. Switches are fantastic for local communication, but they have their limits. They only understand local MAC addresses. If you want to send a packet to a computer on a different network, say, in another department with a different IP address range, a switch just won't do. That's where a router comes in. A router is like the post office for your network, connecting different networks or subnets together. When your packet, destined for that other network, arrives at the router looks at a different address, the IP address. It's the director of cross-network traffic. The router's brain is its routing table. This table is a set of rules and directions that tells the router the best path to reach any given IP address. When your packet arrives, the router performs a lookup in this table. It finds the entry that best matches the destination IP address and determines which of its connections or interfaces leads toward that destination. It then repackages your data with a new local MAC address for the next hop and sends it on its way. This process of hopping from router to router is how packets travel across the vast internet. Now, let's talk about how you connect to the internet from home. Your home network uses private IP addresses, which aren't routable on the public internet. Your router performs a crucial job called network address translation, or NAT. It acts as a gateway, taking packets from your devices and swapping their private IP addresses for its own single, public IP address. It keeps track of these swaps, so when a reply comes back from the internet, it knows exactly which device in your house to send it to. It's like having a single mailbox for your entire apartment building, with a very organized receptionist. To prevent packets from getting lost and looping forever on the internet, they have a built-in self-destruct timer called time to live, or TTL. Each time a packet crosses a router, its TTL value decreases by 1. If the TTL hits 0 before it reaches its destination, the packet is discarded and a message is sent back to the sender. This keeps the internet from getting clogged with lost data. Sometimes, packets are also too large for a certain network path, so routers can break them into smaller pieces, a process called fragmentation, to be reassembled at the final destination. Back in the local network, switches have another cool trick up their sleeves: VLANs, or virtual local area networks. VLANs allow a single physical switch to be partitioned into multiple separate, virtual switches. Devices in one VLAN can't talk to devices in another without going through a router, even if they're plugged into the same physical switch. This is great for security and organization, letting you group devices by department or function, like keeping the finance team's traffic separate from the guest Wi-Fi. Switches also operate in different modes. The most common is store and forward, where the switch waits to receive the entire packet, checks it for errors, and then sends it. This is reliable, but adds a tiny delay. The other mode is cut through, where the switch starts forwarding the packet as soon as it reads the destination MAC address, without waiting for the rest. It's faster, but can sometimes forward corrupted packets. Modern switches are smart enough to balance both. So, let's trace a full journey. You click a link to a website. Your computer creates a packet. The local switch uses the MAC address to send it to your router. The router uses NAT to give it a public IP, looks up the destination in its routing table, and sends it to your internet provider. The packet then hops across several routers on the internet, its TTL decreasing with each hop. Finally, it arrives at the server hosting the website. The server sends a reply that follows a similar path all the way back to your screen. It's a beautiful, high-speed dance of switches handling local traffic and routers directing the long-distance journey. And there you have it. Switches work at Layer 2, using MAC addresses to forward frames within a local network. Routers work at Layer 3, using IP addresses and routing tables to connect different networks. Together, they form the backbone of our digital world. If you found this helpful, give this video a like and subscribe for more tech explainers. Thanks for watching.